Bernard Leclerc from University de Caen. Ah, merci.
Is it not? Maybe.
Yeah. He's going to talk about shifted quantum affine algebra and cluster algebra. Please start.
Thank you. Thank you very much, all of you, for coming. So I'm going to discuss about a recent paper which appeared this spring. This is a joint work with David Hernandez and Christophe Geis. So yes, so the plan of the talk will be the following. First, I will explain some motivations, and I will give an overview of the main result without being too technical and too precise. And then in the second part, I will deal in more details with the special case of SL2, which is easier to explain, and also for which we have complete proofs, because we have also some conjectures which we cannot prove yet. And then so I will explain the general case, the statement of the conjectures, and okay, so motivation and overview. I will start with this picture. So those who have followed my lectures, in particular yesterday, will recognize maybe this quiver. So this is the defining quiver of a cluster algebra. And I will use this notation, this shorthand notation, that A is a cluster algebra defined by an initial seed with this quiver. Right, so yesterday we saw exactly this quiver. It is related with type A3 and a certain level L equal 2, or L equal 1, I think, with my notation of yesterday, rather. So it's some example of cluster algebra, and it turns out it is a very classical example. It already appeared in the very first papers of Kirillov-Reshetnikin, of Fomin-Zelevinsky. So yesterday I explained the relation of this cluster algebra with the representation theory of quantum affine algebras, but in Fomin and Zelevinsky it was a completely different interpretation. So in their paper, this cluster algebra was shown to be isomorphic to the coordinate ring of the group of unit triangular matrices. So here I took type A3, so this is SL4. And so this is the group of all upper triangular matrices with one on the diagonal. So all the stars are arbitrary complex numbers. So if you look at this as from the point of view of algebraic geometry, this is just an affine space of dimension 6. So coordinate ring is only a polynomial ring with 6 variables. So as a ring is not very interesting, but it is the coordinate ring of n, so it has also an action on n on it, and this is making it more interesting as a ring. And well, Fomin and Zelevinsky explained why this cluster algebra is isomorphic to this coordinate ring, and in a sense that is interesting. So why is it interesting? Because this coordinate ring, for more general groups, is endowed with a canonical basis, or rather a dual canonical basis in the sense of Lustig. And it turns out that they conjectured in their first paper that all the cluster monomial of this cluster structure that they put on this ring belong to this dual canonical basis. So this was one of their main motivation. Now, as I said yesterday, we have a totally different interpretation of this cluster algebra in our paper with Hernandez. And so this is as the Grothendieck ring of a certain subcategory of the category of finite dimensional representation of a quantum affine algebra. So here SL4 hat means the affinely algebra associated with this group, and this is a quantum enveloping algebra of it. So we have here a certain big tensor category of finite dimensional representation, which I denote by C. And in there, we can define a certain subcategory. I explained how yesterday, whose Grothendieck ring has also this cluster algebra structure. So this was somehow, yes, we also were able to prove in this paper that the basis of simple modules, the classes of simple modules, which form a basis of this Grothendieck ring, when we identify via this cluster algebra this ring with this ring here, that then the basis of simple module coincide with the dual canonical basis of Lustig. So we have a different interpretation of the same dual canonical basis, if you want, using cluster algebra. So my first question and motivation for the work of today is the following. In what was stated before, would it be possible to replace the group N of unit triangular matrices by the group G of all invertible matrices? So it is known that the coordinate ring of this group G of all invertible matrices, or more generally a group of type ADE, say, has a cluster algebra structure. It was also found by Fomin and Zelevinsky. So the question is there also a possibility of interpreting this same cluster algebra structure on G as coming from some representation of quantum affine algebras? So is there some replacement of the category CQ here? Is there some replacement of this category CQ by some larger category whose Grothendieck ring would fit now C of G, if we replace here N by G, C of G? So this is the first question. And the answer is not yet complete, but let me say it seems so. And I will explain our first step somehow in this direction. And what we have to do, we have to first replace quantum affine algebras by this new class of algebra, which are called shifted quantum affine algebra, and which were introduced in 2018 by Finkelberg and Cymbaluk. And I will explain later how they are obtained, what are the modifications you do to quantum affine algebra to introduce this shift. And the other thing that we have to do is that we have to allow apparently infinite dimensional representation. We cannot just model C of G just with a finite dimensional representation. So this is the main message somehow of the talk today. But now I want to explain a different second motivation, or a second source of questions which led to this work. Mm-hmm. So yesterday I explained that the quiver of this category CQ, or of this cluster algebra, in fact was a finite section of an infinite quiver like this. And actually we could consider bigger section of this quiver. So it was a natural idea for David and myself to consider the full quiver, the doubly infinite quiver, and consider the corresponding cluster algebra. So this is now a cluster algebra in which we have clusters containing infinitely many cluster variables. Okay, and then we can mutate from this initial cluster variables and get still the same type of structure. And in a different paper, also with David Hernandez, we proved that this cluster algebra A infinity, now related with this infinite quiver, contains cluster variables equals to the Q characters of all Kirillov-Reshetikhin modules of CZ. So I need to explain. First, CZ is the subcategory of C, the category of all finite dimensional representation. But in this category, the simple objects are parameterized by some discrete parameters, which correspond to the node of the Dynkin diagram, and also some continuous parameters, which are the so-called spectral parameters, which are families of non-zero complex numbers. So it turns out that for what we are doing, it's better to reduce somehow the spectral parameters to the integral powers of Q, like we did yesterday already. And so this subcategory where all the spectral parameters are integral powers of Q, plus some parity condition, similar to what we did yesterday when we picked one isomorphic component of the quiver, which I defined. So anyway, there is a certain subcategory CZ which contains infinitely many Kirillov-Reshetikhin modules of all possible size, with some restriction on the parameters, but this is not so important. And all the corresponding Q characters. So what are Q characters? Q characters in the theory of quantum affine algebra are the notion which replaces ordinary characters in the Lie algebra situation. So these are some Laurent polynomials, and they describe somehow the structure of the representations. In particular, the number of monomials give you the dimension, and then each monomial gives you the dimension of certain weight spaces. So it's like in the classical theory. So these Q characters are certain interesting polynomials attached to every simple module. And what we were able to do is to find some cluster variables in this infinite cluster algebra, for which by a totally elementary change of variable, so like we just replace one variable by the quotient of two other variables. So these are really monomial transformation, not complicated transformation. We get exactly the Q characters of the Kirillov-Reshetikhin modules. So yes, so this was the result of our paper, and then one remark that we could do also in this paper is that in this cluster algebra A infinity, we could prove, or we could see immediately, that there are also some cluster variables which cannot be Q characters of objects of CZ. For example, the initial cluster variables, they are just given by one letter. So if you want polynomial of degree 1, monomial of degree 1, so this cannot be the Q character of any representation, because it would be a representation of dimension 1, and for UQG hat, there is only the trivial representation of dimension 1. And similarly, if you mutate just one vertex, then you would get something which would correspond to representation of dimension 2, and UQG hat, except for SL2, doesn't have two-dimensional representation. So it was clear that there are also lots of cluster variables for this A infinity, which cannot be represented by, which are not Q characters of objects of this. So the second question which arises, can we specify what are the cluster variables which are Q character of simple objects of CZ? First question. And the second question, is there some representation theoretical meaning for the remaining ones? Okay. And I will start to explain what is our answer what is the answer to the second question. In fact, this answer was given already in the paper of Hernandez, a little before the paper I want to explain today. So let me do it now for any simple complexity algebra, not necessarily SL4. So I pick G, and then the corresponding quantum affine algebra UQG hat. And then I have a similarly defined infinite rank cluster algebra A infinity. I explained yesterday, it's really the same graph as what I explained yesterday. Now we can, in fact, put a grading on this cluster algebra, just the most simple grading, you can just decide that every initial cluster variable has degree 1. And then if you mutate, you will see from the specific form of the mutation relation that every mutated cluster variable will be homogeneous with its degree. So in fact, we get in this way a grading on the algebra and the grading of all cluster variables and all cluster monomial. And the answer to the question number 2 is quite easy to formulate. It says that every cluster variable of A infinity has a cluster expansion with respect to the initial cluster, which is homogeneous of non-negative degree. And then a cluster monomial is the Q character of a simple object in CZ, if and only if it is of degree 0. So yes, so again, this A infinity has a natural Z grading, which is in fact a Z plus grading. And it turns out that the only cluster variables or clusters monomials which have the interpretation of being Q characters of simple finite dimensional representation of UQG hat are the ones for which the degree is equal to 0. So for example, the initial cluster variables have degree 1. They cannot be Q characters. And after one mutation, in general, you get still something of positive degree. So you cannot have Q character. You need to do a certain certain sequence of mutation before you can reach possibly some elements of degree 0. And then, if you do this, you get the Q character of a simple module. So this is in fact a theorem. I put here 3 different papers. So one part was already present in our paper of 2016, which is the easy part, namely that this degree 0 condition is necessary. So the fact that the Q character of the simple object, if it is a cluster monomial, it has to be of degree 0. This was sort of clear from our first paper. But the sufficient condition needed this very deep results of this paper of Kashiura, Kim, Owen, Park, which are related with the monoidal categorification I explained in my lecture yesterday. And then Hernandez managed to reinterpret this in terms of yes, in terms of this problem, if you want. Okay, now question number 3 was, what about the remaining cluster variables and cluster monomials? So, oh yes, so this was just to say that I said it already, if G is different from SL2, every one-step mutation has degree positive, so it is not the Q character of an object in CZ. So question number 3, this is where this shifted quantum affine algebra enter the game. So let me just say for the moment that they were introduced by Finkelberg and Zimbaliuk, and they are denoted by UQG hat mu, and they depend on this new parameter mu, which is an integral co-weight of G. So if G is of type ADE, you can identify co-weights with weights. Then it is just a weight, an integral weight. So we have not just one, but an infinite family of shifted quantum affine algebras. When the parameter is 0, then you recover more or less the same algebra, namely you recover a central extension of UQLG. So LG is a loop algebra of G, and the central extension of the loop algebra of G. It means that the representation theory of this one and of this one are very similar. The only difference is that we have a little more one-dimensional representations here because of these central extensions. But apart from that, of course, you can twist any representation then with these one-dimensional ones, but essentially the representations are the same. So it means that in particular, we can regard the finite dimensional representations of UQG hat, which are the same as the finite dimensional representation of UQLG, as particular case of this shifted quantum affine algebra when mu is equal to 0. Now, when mu is not equal to 0, there are lots of differences, as I will explain later. So Hernandez, after this paper in 2019, in 2020, Hernandez started the study of the representation theory of this quantum affine of this shifted quantum affine algebra, and he was inspired by his previous work, this previous joint work with Jimbo, where they studied the representation of Borel subalgebra of quantum affine algebras. This was the subject of my talk 5 years ago, if you remember. So together with Jimbo, they introduced some infinite dimensional representation of this Borel subalgebra, and then in the very similar manner, Hernandez also introduced some categories containing possibly infinite dimensional representation for this quantum shifted affine algebra, and he denoted them by the letter O. So this O is reminiscent of the category O of Bernstein, Gelfand, which contains at the same time finite dimensional representation of a simple Lie algebra and also some infinite dimensional representation like Verma modules. So here, this is typically what happens with this category O mu. We can form the direct sum of all the category O mu's over all possible weight mu and get a huge category which he calls O shifted. And the reason for doing this, I will explain a little bit later. This is to obtain a multiplication on the Grothendieck group. So we want to have not only a Grothendieck group, but a Grothendieck ring. And if you take only the Grothendieck group of O mu, then you cannot put the product structure. You need to okay. And then inside this category O, you can also consider the subcategories of finite dimensional representation. So C mu for the O mu and CSH for the OSH. So we have these 4 type of categories. And let me add also the following one, where I add this index Z to mean that we further restrict the spectral parameters to be integer power of Q like before. So then we are going to concentrate on these 2 categories, CSHZ and OSHZ. And what Hernandez proved concerning this CSHZ, so the finite dimensional ones, he was able to prove that the Grothendieck ring of this is precisely the cluster algebra A infinity that we had before, and that a cluster monomial of A infinity is the Q character of the simple objects in C mu if and only if its degree is equal to mu. So now degree is, I use different font. Degree is now no longer a Z degree. It's a degree with respect to the weight lattice. So how do you grade? So it's also quite natural. Let me go back to the picture here. So before, the degree I used was a most simple one. Every dot has degree 1. Now I'm using a multi-degree where every dot in the first column has degree the first fundamental weight. And then every dot in the second column, the second fundamental weight. And then in this way, we still get that all cluster variables are homogeneous with a certain weight, mu. And then when you look at the cluster monomial, it also has a certain degree mu. And then this degree mu tells you in which piece of the Grothendieck ring this cluster monomial lives. Yes, so this was beautiful answer. And in fact, it relies also on the paper of Kashiwara Kim O. I don't have time to explain this, but you can check his paper. And so this was a beautiful answer to the question of number 3. But then immediately you want to ask a new question, because his paper was mainly on the category O, not on the category of finite dimensional representation. So in his paper, the category O is really an interesting thing. So now what you want to know is whether the Grothendieck ring of this category O shift also has a cluster structure. So this brings me to the 4th question. What about the infinite dimensional modules, and what about the category O? Can we find a cluster algebra structure on the corresponding Grothendieck ring? And this is where we started to work with Gase and Hernandez, and the answer is yes, as I will explain. And what will be the quiver of this new cluster algebra? It turns out that it's rather easy to describe, starting from the quiver of A infinity. So we want somehow to enlarge this A infinity so that now it corresponds to the full category O. So at the level of quivers, it will be this little operation which I illustrate on the case of SL4, so A3, but the same rule applies for ADE. So you see here in red, I have put the vertices which correspond to the sub-cluster algebra, which is isomorphic to the coordinate ring of N. So we can do this in all cases. And then the operation consists in replacing every red dot. So we have 6 of them, the number of positive roots. We replace it by a pair of 2 vertices. So 1, 2, 3, 4, 5, 6. And here, notice that all the vertical arrows are going up. Now, here, these new pairs, you relate them by a single arrow which is going down. And so here also, you can notice that this big graph is made of triangles. So it's full of 3 cycles. Now, when you replace one red vertex by a pair of 2 vertices with an arrow going down, then you replace one triangle like this one by a 4th cycle like this. And you do this everywhere, you see? So I'm not describing it with a formal definition, but I think everybody can understand how you can deform somehow this quiver to this one. So this one had somehow, this one was a translation invariant. This one is no longer translation invariant. It has this upper part, which is like the same as the upper part of this one. It has a lower part, which is the same. And then in the middle, we have made this little surgery that we have replaced every red vertex by a pair of a red and a blue and a descending arrow, and transform certain 3 cycles into 4 cycles. So that is a way to generalize this to any root system. At least the ADE is simple, and the BCFG, we are still working on it, but we have good candidates. And now I can state the main results. That if we take this new cluster algebra, B infinity, then we are able to construct an explicit injective homomorphism of algebras to the coordinate, to the Grothendieck ring of the category O. And the Grothendieck ring of this category O, in fact, as I said, category O contains lots of infinite dimensional modules. So because of this ring is a ring, you can realize it not as a ring of polynomial, but as a ring of power series now. So in particular, it has a topological ring structure. And so what we have here is not an isomorphism, but almost an isomorphism, namely the image by this ring homomorphism. If we take its closure for this topology, then we get the full thing. So that's the best we can get, because B infinity a priori is just a consisting of well, it's a ring generated by cluster variables, and cluster variables are polynomials, so it cannot contain infinite series. But so it can contain limit of elements, and then yes, in this topology they will coincide. Okay, so now the natural conjecture is that not only we have a natural way of connecting these two rings, but we want also that this homomorphism F sends any cluster monomial here to the class of some simple module. And this is what we conjecture. We conjecture exactly the same property that was proved for the finite dimensional ones, but this is still far from being proved in the case of the category O. The only case in which we can prove it is for G equal SL2, and that's why I will spend some time on G equal SL2 immediately. And finally, you remember the first question, which was, can we replace C of n by C of G? And so the answer to this is that if G is of type ADE, now not only SL2, then this Grothendieck ring contains a cluster subalgebra B isomorphic to the coordinate ring of the open double Brugh-cell. So this is not exactly G, but it's almost G, because this is an open cell. This is a big double Brugh-cell in G. So up to localization, this is isomorphic to C of G. So we can, in fact, find a cluster algebra inside this, which is isomorphic to this. And so I can show you easily how to do that. So this is B infinity, I mean, in type A3. And so, yes, so if we do a little bit of counting of dimensions, so the dimension of n, the unipotent subgroup, is the number of positive roots. So in type A3, the dimension of n is 6. And then the dimension of G will be 6 plus 6 plus 3, which counts for the diagonal, right? So 9. So we need to find something which will have now 6 and 6, 12, and 3, 15. And so we already replaced all the red dots by a pair of dots. So in this sense, we already did the completed the positive plus negative roots, and we still need to add something for the torus. And so the idea is the following: you just cut in this infinite quiver this piece here, and it turns out that this is one of the initial seeds for the cluster algebra on the double Brugh-cell, which was already investigated by Fomin and Zelevinsky. So we recognize here one of the classical double Brugh-cell pictures. And so this is naturally a subalgebra. This cluster algebra is naturally a subalgebra here. So here we want, in this case, we consider these 3 lower blue vertices and the 3 upper dot vertices as frozen variables. We cannot mutate them, and this is exactly the way they appear also in Fomin and Zelevinsky. So if you require them to be invertible, then you get the open Brugh-cell. But if you don't demand them to be invertible, then you get the coordinate ring of G. Okay, so this was a sort of summary of the results, and now I can pass to the more specific construction for the case of SL2. I mean, before that, maybe if you have some questions. No? Okay, then I want to explain to you how we define, because this is a sort of new family of algebra, so probably you have not seen the definition before. So what are these shifted quantum affine algebra? And we will start with the simplest case of SL2. So in my lectures of yesterday, and the week before, I explained that the quantum affine algebra are defined by a presentation, just generators and relation. And the presentation I gave you yesterday is a so-called Drinfeld-Jimbo presentation. So it has finitely many generators, which are in bijection, or I mean in 4-to-1 correspondence with the vertices of the affine Dynkin diagram, right? But it turns out that Drinfeld has also given a different presentation, which is more complicated in some sense because it has infinitely many generators and infinitely many relations, but which is also very useful when you study the representation theory of this quantum affine algebra, especially the finite dimensional representation or the so-called level 0 representation. So this is called the Drinfeld presentation. And it has infinitely many generators, which are denoted by xk, yk, hk, and also these two special generators, k and k bar. Okay, and what kind of relations? Well, the h commute, the h also commute with capital K and capital K bar. So this is like a Cartan part, if you want, an affine Cartan part. And then x k and y k, they have some interesting commutators, which are written like this. So here, phi plus and phi minus are certain polynomials in the h variables, and they are a little bit annoying to define one by one, but they can be defined using a formal power series, a generating series, in this way. So the generating series, for example, for this variable phi plus, you can write like this with a formal parameter u here. And then here you take the formal generating series of the h multiplied by this q minus q inverse, take the exponential. And then this equality means that if you want to calculate phi a plus, so this is the coefficient of u to the a in this series. So you just calculate what is the coefficient of u of a in this series. And remember that the h are commutative. So this is just some calculus, some exercise in formal power series somehow. But still, it's a little bit complicated formula. And similarly for the phi minus, where you replace the generators hk with k positive by hk with hl with l negative, and then k by k bar. So then this type of phi plus and phi minus, they enter this commutator formula. So there are more relations, but I just indicated them with these dots. I don't want to bother you with all the relations. These are the most important for this work of today. Now, if you are a little bit lost with all these elements, let me indicate for you what is the classical limit. So when q tends to 1, in a certain sense, this algebra UQ SL2 tends to the classical UL of SL2. So the universal enveloping algebra of the loop algebra. And what is the loop algebra of SL2? This is generated by elements of the form X, where X is in SL2, and T to the K, where T to the K is a power of a certain formal variable. So xk, in fact, has classical limit x to the tk. So here I'm using the letter x, y, h to denote the usual basis of SL2. X is a matrix with a 1 above the diagonal and 0 elsewhere, y 1 below the diagonal, and h is the diagonal matrix 1 minus 1. So this guy go to the product of x, y, h by certain power of t, and these others have also a nice limit when q tends to 1. So okay, so that's what it is. I mean, this is a definition. Now, this is kind of complicated maybe, but if you have never seen it, but it is very classical and it has been used in hundreds of papers, this Drinfeld presentation. So what I want to say is that the shifted quantum affine algebra now, they will be defined by exactly the same presentation up to 2 little modification. So now we are in the SL2 case. We have to choose an integral co-weight, but an integral co-weight is the same as an integral weight, and an integral weight for SL2 is just an integer. So let's choose m, an integer, and let's give a presentation of UQM now shifted. So you see, the generators are the same letters, etc. Everything is the same. The only difference is here. Before we had b smaller or equal to 0, and here we had u to the 0. So we didn't have this term. So we just introduced some shift in this power series. This is a power series in the letter u, and we shifted by u of m. And then we also shift correspondingly the phi minus. And so now when you calculate phi k plus L or phi plus, let's say phi k plus L minus, then there will be some modification because of this shift. And this is the only modification. No, exactly, not exactly the only modification. You have noticed that before we had here k times k bar is equal to 1. And this is no longer required here. So now k and k bar, their product is not necessarily 1. They are not inverse of each other. We need both of them. And so they play here different role. And so that is the second difference, and that's all. So this is why when you put m is equal to 0, then there is no difference from this side. When m is equal to 0, the only difference is that UQL SL2 is obtained from UQ0 SL2 hat by adding this relation k bar is equal to 1. So you see this is a really very mild modification, and that's why the representation theory are almost the same. But when m is positive or negative, then there will be some totally different features in the representation theory. So for example, when m is positive, then this UQM SL2 hat, it has some interesting new, in a sense, finite dimensional representations. So new in the sense that they may have dimensions which could not appear in UQSL2 hat, like 1 or well, no, maybe I'm pushing it a little bit too far, but let's say yes, it has more non-trivial finite dimensional representation. It's not just by the dimension that you distinguish them, also by isomorphism type. And on the contrary, when m is negative, you can also consider this, and then you can show that it has no non-trivial finite dimensional representation. So when you look at the representation theory of finite dimensional, then you lose all the negative shift. In the negative shift, you can never obtain finite dimensional representation. And this is related to the fact that the algebra, the cluster algebra A infinity, which I had before, you remember, which was the Grothendieck ring of the category C infinity Z. So the category of finite dimensional representation, this was positively graded. So in fact, the negatively graded doesn't appear because the negative shift parameters do not give any finite dimensional representation. Okay, so let me tell you a little more about this. I said that Hernandez defined a certain category O, so I will not give you the complete description of the category O, but I will give you at least the description of the simple objects in this category O. I mean the parametrization of these simple objects, the classification. So first of all, David introduces the notion of highest L weight module. So if we have a representation V of this quantum affine shifted algebra. We will say that it is a highest L-weight module if it contains a vector V and a certain number. I mean, we also have for every k a certain number, complex number psi k, such that V generates the representation under the action of UQM SL2 hat. V is highest L weight. So what does it mean, highest L weight? It means that it is scaled by all the raising operators. So in this setting, the raising operators are the xk. So it is scaled by all the xk, and then it is also a L weight module. And so this is an L weight vector. And this means that it is a eigenvector for all the elements of this sort of Cartan subalgebra, which is generated by the hk or equivalently generated by the phi k. So we want it to be an eigenvector for all the phi k plus. And we call psi k the corresponding eigenvalue. So this is an analog in this setting of the highest weight module in the classical Lie theory. And if this is the case, we will say that the highest L weight of this module, well, what is it? It is a collection of all these eigenvalues. So we collect all these eigenvalues into a formal power series by taking this power series, and instead of calling it psi k, we call it just psi. So psi of z is a generating function for all the eigenvalues on the highest weight vector. So in principle, you can have representation of your UQ SL2, which are highest L weight module with maybe arbitrary, at least you could think, arbitrary highest L weight, arbitrary formal power series here. Now, in fact, in the category O, as it was defined by Hernandez, and again, I'm skipping the definition, but you can check it in his paper. One feature of this category O is that the simple objects will all be highest L weight modules. But the highest L weight will not be an arbitrary formal power series. It will be a rational formal power series. So it will be if you want, the power series expansion of a rational function. So we call this a rational highest L weight. So this psi of z, it belongs to this if you want, but it is an expansion of some rational function in z. And also, what is the m? M here corresponds to the degree of this rational function. And by degree, I just mean that a rational function is a ratio of two polynomials, and I'm taking the difference of the ratio of the degree of the numerator and degree of the denominator. And final condition, you want them to be regular at z equals 0. So z equals 0 is neither a 0 or a pole of this. And now the classification result proved by Hernandez is that, conversely, if you take any rational function Cz of this form, so of degree m and regular at z equals 0, then there is a unique simple object in the category OM with highest L weight psi. And so the classification of the simple object in OM is given like this. Right. So let me denote by Rm the set of all these rational functions of degree m and regular at z equals 0. So in other words, this is a parametrizing set of the simple object in this category. Now we want to introduce some notion of character again. So when we have a highest L weight module, we have the highest weight vector, but then we can also look at the eigenspaces or generalized eigenspaces. I mean, we know that we have this large commutative subalgebra generated by the phi plus, and so we can look at the decomposition of V as a sum of generalized eigenspaces with respect to this commutative subalgebra. And it turns out that the generalized eigenvalues corresponding to all these generalized eigenspaces will again be element in the same parametrizing set. So they will again be some rational function of degree m regular at z equals 0. So let me note that this is something which is different from the representation of from the finite dimensional representation. When you look at the finite dimensional representation already for Lie algebra, then it is known that the highest weight is a so-called dominant weight. And then when you look at the decomposition into weight spaces, the other weights, most of them are no longer dominant. There may be some dominant weight also inside, but in general, you have non-dominant weights which appear in the decomposition. And here, everything, there is no notion of dominant. So every weight can be the highest weight of a simple module, if you want. Okay, so this is what we can say. And so because of this, now we can form the following. So I should have said, maybe I didn't mention it, but this generalized eigenspaces, even if the representation is infinite dimensional, all these generalized eigenspaces are finite dimensional. So we can form a certain series generating function, if you want, for the dimensions of all the generalized eigenspaces. And we call it the Q characters, the Q character of V. So here, this symbol is, if you want, a symbol of some formal variable phi, which you can represent by element like this, psi of z, some rational functions. But here we take them as formal variable, and you can multiply them, add them in the natural way, the way you add or multiply two rational functions. But we can also regard them just as new indeterminates. And then you get some expression like this, which in general will be an infinite series, because the function, the representation V will be in general infinite dimensional. And what Hernandez proved is that the map which takes a representation V to its Q character induces an injective map on this Grothendieck group. So in other words, if two representation V have the same, what should I say? Yes, if two representation V have the same class in the Grothendieck group, then they have the same Q character. And if they have different classes, then they have different Q characters. So this means that you can look at the big power series ring in this variable phi, and you can embed this abstract Grothendieck ring as a certain subring inside this polynomial or power series ring, right? So this is the way we want to look at now at this Grothendieck ring, not just abstractly, but also as realized by some formal power series. Okay. Now I want to give you, so I gave you the classification of the simple objects, and I want to give you the most basic simple objects in this category O. So the first thing you can take, you can take the shift m is equal to 1. So m is equal to 0, I explained there is no difference with the classical theory. M is equal to 1. Then you can take the following example of element in R1. R1 is a set of rational function of degree 1. So you can take a polynomial, just a polynomial of degree 1. You don't want it to be singular at z equals 0. So this means 0 should not be root. So in other words, you can normalize it so that it is of the form 1 minus az, where a is complex number, non-zero complex number. And then what David proves is that the corresponding simple object is very simple because it is one-dimensional. It is one-dimensional. In other words, it reduces to the highest weight vector. And so it is killed both by the raising operator sk and also by the lowering operator yk. And it is an eigenvector for the, and so in other words, its Q character is reduced to just one monomial, namely this class of psi A. So in this way, you see that already for m equal 1, we get a bunch of new finite dimensional representations. Now, if m is equal to -1, you could do the inverse of this. So instead of taking 1 minus az, we take 1 minus az inverse. So this is now a rational function of degree -1. Let me denote it by psi a inverse for short. And then what Hernandez showed is that this is now the highest weight of an infinite dimensional representation, but not too bad. You can write explicitly its Q character in the following form. So the highest weight monomial is again given by the variable psi a -1 itself. And then you have a sum like this, a regular sum, where the letters AA denote the following monomial, Laurent monomial in the variable psi a. So in other words, for example, this one means the rational function 1 minus a q square z divided by 1 minus a q minus 2z. So it's in other words, this is a rational function of degree 0. So every a or a inverse corresponds to an element of degree 0. So in this series, you have only elements of degree 0. So degree 0 times degree -1 gives you something of degree -1. This is consistent. Right. So these two families of modules are called the prefundamental modules, and they turn out to be somehow the main bricks for constructing all other representation of UQSL2 hat. Yes, in order to construct all the others, you need this fusion product operation, which was also defined by Hernandez in his paper. So I said before that if you want to have a multiplication in the Grothendieck group, you need to put together all this category OM for all possible M. And the reason is that the fusion product works like this. It takes an element in OM, another one in ON, and the result is in OM plus N. So it's a little bit like when you look at representation of symmetry groups, you don't study just the representation of the symmetry group SM. You study the representation of all symmetry groups simultaneously, and then you have an induction product which goes from SM to SM plus N or yes. So exactly the same idea. And so this provides a ring structure on the Grothendieck group of OSH, which is, as I said, just the sum of all these Grothendieck groups here. And this multiplication is compatible with the product of formal power series. So in other words, the Q character of the fusion product is a product of the Q characters. Right. And now I can give you a more precise statement in the case of SL2. So in the case of SL2, yes, we can say that the Grothendieck ring K0OSH is generated as a topological ring by just the Q characters of the positive and negative prefundamental. So you have some, you want to consider a ring with elements in all possible degrees, positive and negative. And so what it says is that this ring is generated by the elements in degree +1 and the elements in degree -1, right? And now we can be more explicit and give some presentation of this ring. So for short, I will use the following notation. The Q character of L psi Q qk, so this is a positive prefundamental representation, we will call it q plus k, and similarly q minus k for the negative prefundamental representation. So we can show that this q plus k and q minus k verify the following relations. Q plus k times q minus k is equal to 1 plus q plus k plus 2, q minus k minus 2. And then if we look at the subcategory in here where we put this index z, so the subcategory where we restrict the spectral parameters to be integral powers of q, then this is generated by this q plus k and q minus k, where k go through the even integer in this case, and this is a presentation of this ring. And as I said before, this contains the image of this infinite cluster algebra, and so in particular we can prove in this case that the cluster variables are, or their image, let's say here, the image of all the cluster variables are of three types: either the q plus k, the q minus k, or the q characters of these highest weight modules. And here you can see that this is just the ratio of a psi and another psi. So this means that this is of degree 0. And in fact, this is the q character of a Kirillov-Reshetikhin module for SL2. So for SL2, the cluster variables are quite simple. These are just the positive prefundamental, negative prefundamental, and Kirillov-Reshetikhin module. The clusters are more interesting, of course. You can then, the cluster will be some infinite collections of these variables, and then you cannot take any collection. You have to take them so that, yes, some conditions are satisfied. So let me show you the initial seed. So initial seed of this cluster algebra B infinity, you remember how we obtained it. We started from the initial seed for A infinity, and then we blowed, yes. Now, in the case of SL2, what is the quiver for A infinity? This is just one column, like this, because SL2 is of rank 1. Linking diagram is just one vertex. So one infinite column like this with arrows going up. So there is only one red vertex, and this one red vertex we replace by, so you get this. You have one arrow going down between two vertices, and then the rest go up and down. And now this is telling you how you can attribute to each vertex a certain cluster variable. So in this case, for this initial seed, all the cluster variables are only positive prefundamental above this special middle part, and then negative prefundamental below. And the spectral parameter go regularly 0, 2, 4, 6, and then -2, -4. So nothing simpler than this. Now, notice what happens when we do a mutation, for example, at this red vertex. So you can calculate, I mean, in your head. I don't even have to write it on the board. What is the mutation at this vertex? So if you call, let's say, x the new cluster variable, then we will have the relation x times q0 plus is the sum of two monomials. One monomials correspond to the outgoing arrow. So it will be q plus 2, q minus 2. And then the second monomial corresponds to the ingoing arrow. But this is the source. There is no ingoing arrow. So the second monomial will be 1. So we will have x times q0 plus is equal to 1 plus the product of these two. But this is precisely one of these relations, this relation for k equals 0. So this means that the mutated variable, I started from q plus 0, the mutated variable will be q minus 0. So it means that in this, if I mutate here, what I get is this, that the q plus 0 is replaced by q0 minus. the positive prefundamental replaced by a negative one. And at the level of the quiver, you replace this sink, this source by a sink. So what do you get? You get exactly the same configuration, but shifted up one step. And if you would mutate at the blue vertex, then it would be similar. But now you replace this q minus 2 by a q plus minus 2, and then you have brought this middle part one step lower. So this is really the feature which will happen in all ranks. In all our ranks like this, if we mutate at red vertices or at blue vertices, we shift the seed up or down. And this is a very interesting feature of this class of cluster algebra. Right. So now I have already finished my time. So maybe in 2 minutes I will explain I have only 2 slides now, or 3 slides. So I just want to say that in the general case, we do more or less the same. We start now from the Cartan matrix of G, which is the transition matrix from simple roots to fundamental weights. If we are in the non-simply laced case, we may need the length of the alpha I, but let's forget about this. We have the Weil group, which is generated by the simple reflection. And then similarly, Frenkel, Thimbalyuk, and Hernandez introduce a certain category O shifted for this setting G. And Hernandez has classified the simple objects of this category. Now you have again the same type of notation, psi plus and psi minus, but now this psi have another index I, which corresponds to the vertices of the Dynkin diagram of G, right? For every vertex of the Dynkin diagram of G, we have a psi I like this. And so the let's say now the highest L weight will be not just one rational function, but a collection of I rational function. So it will be an element in CZ to the I. Here, capital I means the set of indices of the Dynkin diagram. And the prefundamental one, they will be trivial at every position except for the position I, where we will have 1 minus AZ for the positive one and 1 over 1 minus AZ for the negative one. And then this is a classification, so we can parameterize the simple objects by this psi. And we have the positive prefundamental module, which are just the L psi I, which are again of dimension 1. And we have the negative prefundamental, which are again of infinite dimension. We have also a fusion product, and this becomes a topological ring, which is generated by the classes of positive and negative prefundamental modules as before. And we can also embed this ring into a ring of power series by using the notion of Q characters, which is defined in the same way. So now one more ingredient comes from a paper by Hernandez and Frenkel, a recent paper on a Weil group action and the relation with some new systems of new systems of functional relation called QQ system. So, okay, in short words, Frenkel and Hernandez have defined an action of the Weil group of the Lie algebra G, so the finite Weil group, on this ring of Q character, or on Grothendieck ring, if you prefer, which has the following extremely interesting properties. This was their motivation. If you look inside OSH, we said that we have the category of finite dimensional representation for the shifted quantum affine algebra, and this contains the category of classical finite dimensional representation, so the one which corresponds to the parameter 0, right? So what they say is that the action of W on pi is such that the invariant for this action are exactly the Q characters of this finite dimensional representation. But all the others, of course, they are not fixed by this action. Now, using this action, you can start from the character of a positive prefundamental module. So this is just one term. You start from the simplest one, the simplest which belongs to this guy here, the one-dimensional positive prefundamental. And then you apply elements of this Weil group, and then you get some new elements. So they denote them like this, and they call them Q variable, and they show that this element, first of all, they depend only on the chamber co-weight here, and more interestingly, that they satisfy the following relations. So these relations are sort of in the same spirit of the T system that we mentioned yesterday, but slightly different. They use the Weil group. So I don't want to describe them so much here because of lack of time, but you have some relation like this. And when we are in simply laced type, the monomial in the right-hand side is just like in the T system, easily described in terms of the Cartan matrix. So we have a system of equations like this satisfied by these guys. And again, if you bring this second term to the right, then you recognize a relation of the form product of two things is the sum of two monomials. So this is again a sign that maybe cluster algebras are around. And so the main result now, I said that already stated that we can attach a certain cluster algebra, infinite quiver, and so cluster algebra to Cartan matrix. And now we can also define this injecting ring homomorphism in such a way that the initial seed consists only of these particular Q variables. But now this is a little more complicated than SL2. We have not only Q plus and Q minus, we have a family of Q which depends on the Weil group and also on the vertices of the Dynkin diagram. So they are labeled like this. And instead of giving you the precise, I will just finish with this example. So in type A2, you see in the upper part, so this would be the quiver for B infinity. You know, A2 is SL3. So now the unipotent group is of dimension 3. So we have to double these three vertices like this, and then yes, so it's consistent with the previous description. So above the middle part, you have only positive prefundamental representation. Below the middle part, you have only Q variables. So yes, you have only these Q variables corresponding to the maximal Weil group element. And this turned out to be equal to the Q character of the negative prefundamental. And then in the middle, you have some increasingly bigger Q variable coming from the action of the Weil group like this. And just for fun, I can show you what we expect to be. So this is not yet in our paper. In our paper, we only wrote the simply laced case up to now, but this is what we expect to have in type B2, for example. So slightly more complicated combinatorics, but still it should be working. And so I finish here. There is some references.
Any questions or comments?
Yes. Yes.
So the QQ system is QQ system related to, for example, T system or usual?
So with T system, I don't know. I don't think so. It's the same flavor, but it's not. I don't know how to degenerate it to a T system or relate it in some way to a T system. To me, it's a different
new system.
It's a new system, I think. Yes, it's a new system. In fact, it was Frenkel and Hernandez obtained this system in 2 steps. In their first paper, they only had the part of the of the QQ system where W is equal to the unit element in the while group. So there was no while group, just SI, if you want, and so maybe this initial QQ system could be related to a T system. I don't know, but then in the most interesting extended QQ system, if you want, then you have this while group element which also enters the picture, and so I don't see how to imitate this in the QQ system or T system or T system in the Q system or T system or Y system. There is no while group. If I'm
Any more? Actually, I have one. So the last slide, the main results that you fix the reduced expression. So then the coordinate ring related to that cell attached to that kind of W are related to the.
So one important result is that yes, initial seed. In fact, we get initial seeds for any reduced decomposition. And so the point is that you can pass from one initial seed to another by a finite sequence of mutations. So these different initial seeds define the same cluster algebra. So these are just two different seeds inside the same cluster algebra.
My question is that originally you want to look at coordinate ring.
A coordinate ring of
so
G.
What's the role on here? Yeah, coordinate ring of G.
Yes. So exactly. So I said that what we recover by taking this finite part here. So in this case, we would take these 6 vertices plus these 2 vertices here. So if we look at this finite cluster algebra generated with this initial seed, so this will be one of the initial seed of Fomin-Zelivinsky for the cluster algebra of the group G. And more generally in their paper, if you look at it, they call this double Breuer cells. So the double Breuer cells, they depend on 2 elements of the while group, and they have described some seeds attached to any pair of reduced expression for both elements. So in their paper, you can take one element, one reduced expression, another element, another reduced expression, and then you get a seed, and all these seeds are related by some finite sequence of mutations. So all of them define the same cluster algebra. And the one which we are using here are some particular ones where we, first of all, we take the while group elements to be W0, W0, so the big double Breuer cell, and we take the same reduced expression for both. Instead of them, in their paper, they choose arbitrary reduced expression, and we took, and then this is exactly the same. So if you want, and if you look at our paper in the last part, we explained that you could replace formally all this part by something which has the same shape, but now where the vertices correspond to some generalized minors inside the coordinate ring of G, and they satisfy exactly the same cluster algebra structure. So this finite part will look exactly like that. So maybe your question is, do we have a categorification?
Well, actually, this was the second one, but
so this is the hope, but at this moment there are too many conjectures to be able to state. But what I expect indeed is that if we look at the subcategory of this O shift generated just by this finite part, so if we look at the small, in a sense, subcategory, which is generated as a tensor subcategory or as a monoidal subcategory by just this finite part, then this should be a monoidal categorification of the coordinate of the cluster structure on the coordinate ring of G. But there are many things to be proved yet. It's yeah.
Conjecture. Thank you. Anything more? ズームの方は質問ございますでしょうか? I have much more fundamental question, but later. I don't know. Okay, no questions. So let's Bernard. Let's thank the Bernard again.
Oh, sorry.